Welcome to Module 5, Lecture 4. We're going to be deriving the Hadamard identity. This is the third of our 4 fundamental operator identities. And this is the one, along with the Leibniz identity, that we use more than anything else. So, as an introduction to this, you might be wondering who Hadamard is and why his name goes with this identity. I actually have no idea. As far as I can tell, he had nothing to do with it. The research that I've done indicates that a man named Campbell is the person who's responsible for this identity. And it seems very odd that the name is given the Hadamard Lemma. It appears that this is something that happens very common in science, where the work of one person gets recognized by a different person, and a different person's name goes with a particular effect. So I want to emphasize how important this particular identity is. We're going to be employing it many, many times in the class. The derivation is a bit long, and we're going to do it two ways. First, we're going to do it algebraically, and then we're going to do it with calculus. The reason why we're doing it two ways is that the identity is so important. I want to really make sure that you understand it. The algebraic derivation uses a proof by induction, and there's a fair amount of long algebra in that. So brace yourself. We have a lot of complicated work to go, but the prize at the end is well worth it. So the Hadamard lemma takes the following form. It looks at the 3-operator commutator product, exponential of an operator A, operator B, exponential of minus the operator A. And it says that that combination, when you have 3 operators in that form, you can write it in something that might be a bit reminiscent of an exponential, but really looks quite a bit different. It's a sum n equals 0 to infinity. There's a 1 over n factorial. And then there's an n-fold nested commutator of A's commuted with B in the center. And this is something that I'm sure many of you have never seen. So let's actually take a look at what the first few terms are. So obviously, when n is equal to 0, there's no nested commutator. And that first term is the operator B only. The second term has n equals 1, and then there's one nested commutator, and 1 over n factorial is 1, so that's going to be plus the commutator of A with B. And then the third term is n equals 2, and that has a 1/2 from the 1 over n factorial, and then it's the commutator of A with the commutator of A with B. And we're going to see exactly what that is by expanding it out as we go through the derivation. But then the fourth term would be a 1 over 3 factorial, and it would have this 3-fold nested commutator with a commutator of A with a commutator of A with a commutator of A with B. And so you can see it does get complicated pretty quickly. So this nested commutator is something that you probably haven't seen before or seen this notation, but it really just means I'm making yet another commutator with A with whatever I got from a previous commutator. And so we're going to just carefully go through the derivation of this as we look through every step. Okay, how do we work on this derivation? Well, as with many of the things that I cover for you in the class, essentially you just start and you use what you know. So what do we know about a product that looks like e to the a, b, e to the minus a? Well, pretty much the only thing we know is we know that there's a power series for the exponential, and that is one way that I can think of evaluating the exponential of an operator. So let's just plug in the power series on both sides. And what we find is on the left-hand side, I get 1 plus a plus 1/2 a squared plus 1/6 a cubed and so forth. On the right-hand side, because of the minus sign, I get an alternating series there. So it's 1 minus a plus 1/2 a squared minus 1/6 a cubed and so forth. So how do I work with this object? Well, there are many, many terms in here. The best way to organize ourselves is to collect all the terms that have the same number of powers of a. And so I'm going to carefully go through that. So the terms that have no powers of a occur when a 1 from the left meets the b meets the 1 from the right. And that's the first term, and that's an operator b. Then the terms that have one a term have an a on the left, a b on the right, and b in the middle and a 1 on the right, and that would be the term AB. And then there's one more term which has a 1 from the left, a b from the middle, and a minus a from the right, and that gives minus BA. And so you can see that first term is indeed the commutator of A with B. Now, for the second order term, we're going to start from the left with a 1/2 a squared times the b times the 1. And then we're going to have minus a times the b. I'm going to have a plus a times the b times the minus a. And that will give us a minus 2ABA when I take into account the fact that I pulled a factor of 1/2 out in the front. And then the final term takes a 1 from the left, a b in the middle, and a 1/2 a squared on the right. So that will be plus 1/2 BA squared. And that's the collection of terms that we call n equals 2. For n equals 3, I start with a 1/6 a cubed, a b, and a 1. And then I have a 1/2 a squared, a b, and a minus a. And then I have an a b, and a 1/2 a squared. And finally, I have a 1 and a b and a minus 1/6 a cubed. And that collects the 4 terms that are listed below with n equals 3. All right, so I have copied that extraction of those first 4 terms, and now let's start looking at unpacking them. So we're going to look at each term one by one. N equals 0 is obviously b. For n equals 1, we already showed that's already in the form of the commutator of a with b. Let's look carefully at n equals 2. So the term is 1/2 a squared b minus 2ABA plus BA squared. You might think of the next thing I'm doing as a add 0 trick, but I'm actually just splitting that minus 2ABA term into 2 terms that are just minus ABA. So I'm going to have a minus ABA and a minus ABA. And now what I'm going to do is I'm going to collect terms. So I'm going to collect an A out of the left-hand side of the first 2 factors, and I'm going to collect an A out of the right-hand side of the next 2 factors. And you can see when I do that, I clearly now am getting a commutator on both sides. But in one case, the commutator is on the right, and on the other case, the commutator is on the left. So let me simplify that, put the commutators in. Now look carefully at this. I have an A multiplying on the left of the commutator AB minus the commutator AB with an A multiplying on the right. And indeed, that is another commutator. It's a nested commutator now of A with the commutator of A with B. And so we've now verified the second order term. Okay, let's go to n equals 3. This has a lot of terms. It's going to take us a little bit of time to unpack it all. The first thing that we do is we do the separation, but instead of making 3 terms, I separate it into minus 1 and minus 2. And I separated it into plus 2 and plus 1 of each of those terms. And now I'm going to do the same grouping. I'm going to pull a factor of a squared out of the first 2 terms. I'm going to pull a factor of a out from the right and out from the left of the next 2 terms. And I'm going to pull a factor of a squared out from the right on the last 2 terms. And so you can see when we do that, we organize it in this fashion, and you can see in each case I get some nice commutators coming out after doing that factorization. So let's rewrite those commutators as the commutators. And now what I'm going to do is now I'm going to split that middle term into a minus 1 and a minus 1. And I'm going to now look at the fact that I can pull out a factor of a from the left on the first two terms. I'm going to pull a factor of a out from the right on the last two terms. And you can see then that I have left a commutator of a with the commutator of a with b, and a commutator of a with the commutator of a with b in both of those terms. And so we can put that nested commutator in. Now look again, what do we have? Well, we have an a on the left times this n equals 2 nested commutator minus the n equals 2 nested commutator with an a on the right. And indeed, that is another commutator. So that becomes a nested commutator again. And we get our third order term in exactly the form that we said it was going to be. And you can see that a pattern is developing. But we can't just say that a pattern has developed and end our proof. We actually need to complete the proof by using a proof by induction. So I'm going to take you through the steps that give you a proof by induction. It's a counting exercise to find all of the terms that have n a hat terms in them. And we do what we just did on the previous page. We take the mth term from the left and the n minus mth term from the right, and that will have a total of n a terms in it, a operator terms, and then we sum m from 0 to n to pick up all of them. So there's a total of n terms that have a hat to the nth power in them. And so as we collect those, so the terms on the left will have, you can see it's from the exponential. So there'll be a 1 over m factorial and an a hat to the m from the terms that we pick from the left. Then there's a b in the middle, and then there's a 1 over n minus m factorial times a minus 1 to the n minus m times an a hat to the n minus m from the terms that we pick from the right-hand side. And so we just multiply all of those together, and we sum from m equals 0 to n, and that is the term that contains n a hat terms. You can easily see by looking at the powers that the total net powers of a hat are n in number for each term in the summation. Okay, now, the induction step says that that thing must equal 1 over n factorial times this n-fold nested commutator. And so that's what we need to prove. Now, let's take a look at n equals 1. When n equals 1, you see I have two terms in the sum. I have the term when m equals 0, and I have the term when m equals 1. And we've gone through this derivation before, and we find that the base case, when n equals 1, does indeed give us this commutator, because I get an ab minus a ba, and that's the commutator of a with b. All right. Let's move on to the general case. We're going to prove it for the case with n, and we're going to assume it holds for all n up to n minus 1. All right, so what we're going to do is we're going to take the expression that we have and we're going to multiply it by 1. That's an n divided by n. You're going to see in a moment why I chose that factor. And of course, I don't expect you to figure out that that's the right factor to work with. At the moment, just watch what I'm doing in this derivation and be sure you can follow everything. The next thing we do is a add 0 trick. And so what I'm going to do is I'm going to add m and I'm going to subtract m. And again, it might not look like this is an obvious thing to do, but you'll see why it is in probably the next two steps. So the next thing we do is we distribute the sum. I'm going to collect the m over n term in one sum and the n minus m term in the second sum. And so you see we now have these two sums, the sum m equals 0 to n with a m over m factorial, and the sum m equals 0 to n with a n minus m over n minus m factorial. They each have a 1 over n out in front because we had a 1 over n that we pulled out from our multiply by 0. Now, let's look carefully at the term on the left. When m equals 0, that term is 0 because it's multiplied by m. So I can actually replace the m equals 0 by a m equals 1. Let's look at the term with, on the left-hand side. There, when m is equal to n, that numerator term, n minus m, is equal to 0. And so I can replace that limit by n minus 1. And so I'm going to now replace those limits. And so you can see on the left-hand side, I'm going from m equals 1 to n. And on the right-hand side, I'm going from m equals 0 to n minus 1. Okay, now I'm going to do a index shift on the left-hand side. I would rather have that summation go from m equals 0 to n minus 1. So I'm going to redefine m by shifting it. M goes to m plus 1, and then my m index has to go from 0 to n minus 1 to cover the same ground as the index did when it runs from 1 to n, because I've added 1 to each index term. Please be sure you understand that. Now, all that I have to do is I have to take that summand and I have to shift m goes to m plus 1 everywhere. Okay? So, I'm sorry, I'm going to be doing that in just a second, but first I just simplified the factorials. You can see on the left-hand side that m gets rid of one of the terms in the m factorial, it becomes m minus 1, and the n minus m gets rid of the last term in the n minus m factorial, it becomes n minus 1 minus m factorial. So we've done that. Now we're going to do that shifting, like I said, in the second term. I'm going to shift m goes to m plus 1 in the summand, and boom, there you go. I get now a 1 over m factorial. It becomes n minus 1 minus m factorial. It's minus 1 to the n minus 1 minus m. I get an a hat to the m plus 1, and I get an a hat to the n minus 1 minus m. Okay, I just have to go through and shift m goes to m plus 1 in every term in that summand. Let me go back again and show you what it was before I did the shift. And now here's what it is after I do the shift. Okay? Now, what we're going to do is we're going to reorganize this, and we're going to factor out a factor of a hat from each side. The term on the left gets it factored out on the left, and the term on the right gets it factored out on the right. And you can see what is left is this summation for the case n equals n minus 1. Look carefully at the term above. If you substitute in n minus 1 in the top term, you see you get this thing that has this underbrace that says case n minus 1. Now, in the induction proof, we assume that our induction hypothesis holds for the case n minus 1. So I can substitute in the induction hypothesis for n minus 1 into that. And it says it'll be a nested commutator, an n minus 1-fold nested commutator of a's with b at the end. And so we substitute that in. Now, and it has a 1 over n minus 1 factorial as well. Okay? Now, we've done that substitution. Now, look at what we've got. The 1 over n minus 1 factorial times a 1 over n. That's going to give me a 1 over n factorial. I get that on both terms. And then you see I have an a hat to the left multiplied by the nested commutator minus the nested commutator times an a hat on the right. And that indeed is a commutator of a hat with that n minus 1-fold nested commutator. And so we get 1 over n factorial, this n-fold nested commutator. And that's it now. We're done. That has done the proof of the Hadamard identity. Okay, I hope that now you have a better feeling of what this nested commutator is. I hope you also have a clear understanding of how this works. This is a very important identity. Not only is it our third fundamental operator identity, but we are going to derive two other corollary identities from it. One is called the braiding identity, and the other is called the exponential reordering identity. Those are two problems you're going to have on the homework exercise for you to complete. And so now let me summarize the algebraic derivation. It was a lot of work, but we only used add 0 and multiply by 1 and some simple rearranging to do it. So this was not something that was particularly sophisticated to go through. The final result is this interesting term that kind of looks like an exponential summation, but it has these nested commutators in it. All right, you can now take a break because this is a long lecture. You can take a break if you need to, but we're now going to finish up with the calculus derivation. This will be quite a bit faster than the algebraic derivation. So to prove this by calculus, we define a functional operator relation that is very similar to the one that we want to prove, but we've added an x into the exponent. So it's exponential of x times a hat and exponential of minus x times a hat. And we call that operator function f of x. Now, I didn't put a hat on that, but that thing is an operator. And again, we're going to now expand this function in a Taylor series. I'm operating under the assumption that such a Taylor series exists. And what we have when we operate it expanded in a Taylor series is it's the sum n equals 0 to infinity, 1 over n factorial f sub n times x raised to the nth power. Our goal is to find those coefficients f sub n. And so the strategy is we're going to take a derivative, and we're going to do it in two different ways and equate those two different ways of taking the derivative. So the first thing we're going to do is we're going to work from that top equation, from that functional form. Now the derivative of an exponential is just the same as the derivative of a normal function. D by dx of e to the x a hat is going to just pull an a hat down. And because a hat commutes with itself, and in that exponential I just get powers of a hat when I look at the expansion, I can put that a hat on the left-hand side or on the right-hand side. Similarly, on the second term, when I have d by dx of e to the minus x a hat, that's going to pull out a minus a hat. And again, I can put it on the left or on the right. Now, for the term on the left, I'm going to pull that a hat out to the left. And for the term on the right, I'm going to pull the minus a hat out to the right. And so you can see this is what we get. And now what I'm going to do is I'm going to put back in the definition of f of x. You see I have an f of x on the left. It's the left part of the left-hand term, and I have it on the right. It's the right part. It's the left part. I'm sorry. It's the right part of the left-hand term, and it's the left part of the right-hand term. And so I can put in that f of x, and you can see that becomes the commutator of a with f of x. Okay, so that concludes the first part of the derivation. Now I also want to take the derivative one other way, and how do I do that? I take it from the form from the Taylor series. So now we take that Taylor series, we take the derivative. That requires me just to take the derivative of x to the n. That's going to give me an n times x to the n minus 1. You see the n will cancel one term from the n factorial, make it n minus 1 factorial. And now I'm going to do the exact same shift. This is now a sum that goes from n equals 1 to infinity, because previously, if you look here, that n removes the term with n equals 0. And so there is no term with n equals 0 anymore, so the sum only goes from n equals 1 to infinity. And so I'm going to do that same shift. I'm going to let n go to n plus 1, and then my summation will go from n equals 0 to infinity. And I simply go in and shift every index in there by n goes to n plus 1. And so I get a 1 over n factorial, I get a f of n plus 1, and I get an x to the n. Let me show you the previous version again so you can see how that shift works, and that's the shift. And now I have calculated this derivative in two different ways, and so I simply equate them. Now I'm going to go back and I'm going to put that expression for f of x as a Taylor series into the commutator. And now I'm going to pull the 1 over n factorial, the summation, and the x to the n out of that commutator because those are not operators, and so they can just be pulled out of the commutator. And you see now I have this relationship, and we're going to make the assumption, which is a very good assumption, that each of those coefficients are equal to each other. It's the only way for this equation to hold for all x. And so what that means is we've derived a relationship that f to the n plus 1 is equal to the commutator of a with fn. Okay, we're almost done. We have just a couple more steps. So let's take a look at what happens when n is equal to 0. Well, we already know what the first term in this expansion is. It's just b hat. Because if I look at an expansion of those exponentials, each of them has a term that starts with a 1. And we saw this before when we were doing our algebraic proof. So the first term is f0 equals b hat. Now I calculate f1 from this recurrence relation. f1 is equal to the commutator of a with b, because f0 is equal to b. And then f2 is equal to the commutator of a with f1, but f1 was the commutator of a with b. And you can see here, this is a recursion relation that can very easily be solved for the general term. The general case is going to give me that fn is the n-fold nested commutator of a with b in the center. Okay? And that, of course, then provides the derivation. You might not recognize the derivation exactly yet, but all we have to do is after we plug into that Taylor series, we simply set x equals 1. And when we set x equals 1, you see we then have derived the Hadamard identity again. Okay, I hope you've been able to follow this derivation of the Hadamard lemma. The Hadamard lemma is, again, one of the most important identities that we're going to be using in the class, so I really want to be sure everyone can follow it and understand it. I know that this lecture was a bit long today, Most lectures are not going to be this long, but whenever you have a long lecture like this, you can always pause in the middle and then come back to it later after you've had a little bit of a break. And this was a video that had a nice breaking point when we changed from the algebraic derivation to the calculus derivation. So I hope you were able to follow this and understand it. You can go back and slowly go through any parts that you might have had trouble with. It really is important that you understand both how the derivation works and also how we will use this result in our work as we go forward. And you're going to learn that second part by going through examples that we're going to be working with, starting with the material that we're going to have in class following this lecture. And that concludes Module 5, Lecture 4.